So, what we have learned from last class about the radial wave function and radial distribution of hydrogen like atom. Okay. So, we have learned from radial wave function and radial distribution basically what we have seen for only for a state means L equal to 0, this wave function is not equal to 0 at r equal to 0, and also it is independent of theta and phi, right. So, this is important information we got from the wave function, and this result plays an important role in the theory of hyperfine structure. Okay. Second information we got that for L is not equal to 0, r to the power L which is in wave function, radial wave function. So, is not equal to 0. Okay. So, for smaller value of r means in the vicinity of the nucleus and the higher value of L. Okay. So, psi n L m, so wave function is very small, it is almost 0. Okay. Why it is so that I mentioned that this is because of centrifugal barrier or force terms. So, probably remember this kind of term came in the when we are solving the wave function, okay, Schrodinger equation. So, there one term was there, energy term, one energy term was there, right, E, and another term was there, this potential energy V r, okay, and there another term this L plus 1 H cross square by 2 mu r square, this another term was came there. So, this 3 term was there. Okay. So, this term is equivalent to a potential energy, its potential energy is basically barrier. Okay. Kinetic energy is helps to overcome the barrier. So, this term came with the in the same way as the potential energy. Okay. So, this because of this barrier, it is basically because of centrifugal force. Okay. The effect, so it is effective, this is the effective potential, this term together with the potential between the nucleus and the electron. Okay. So, what was that potential? Z e square by r, Z e square by r, okay, and with that term another this L plus 1 H cross square by 2 mu r square. So, that term also comes. So, this together is called the effective potential, and this in that effective potential, because of this effective potential where this term centrifugal barrier term is there, and that prevents the electron from approaching towards the nucleus. Okay. And then another information we got that associated Lagrange polynomial, this is a polynomial of degree n r. N r is basically n l n plus L minus 2 L minus 1 plus 1. So, this basically equal to n minus L minus 1, that equal to n r we have written. So, this n r signifies that the number of radial nodes, okay, means this wave function will be 0 at where that is called the nodes. Okay. When we plot wave function as a function of r. So, that we have seen, and we have also seen that this density probability, that is DNL, it will exhibit n minus L number of maxima. Okay. So, what does it mean? So, you will have n number of means n minus L minus 1 number of nodes, okay. Then you will have antinodes, okay, or maxima, that is just whatever the number of nodes plus 1, okay, nr plus 1 number of maxima or node antinodes you will see. Okay. So, that is what we have seen number of I think just number of antinodes or maxima. In this case it is the nr is 0. Okay. So, this maximum is 1, okay, nr plus 1. So, this 1, so 1. So, nr here in this case 1. So, this nodal point is 1, but maxima will be nr plus 1, okay. So, 2. So, here we are getting 2 maxima. In this case we are getting 3 maxima. Nr is basically in this case nr equal to 2, okay, nr equal to 2. So, 2 nodal point. So, maxima you will get 3 because nr plus 1. So, you will get 3. So, as I mentioned that if you know the number of nodes, okay, so then you can draw the wave function and this probability density. You can basically draw the nature of the curve, okay, without looking at the exact form of the wave function. Okay. So, these are the information we got. So, now we will study we will see the angular dependence of the wave function, angular dependence of the wave function. So, radial part we have seen, radial probability density. Now, angular dependence of the probability density. So, probability density is as we have seen this defined like this. So, here phi that we have seen e to the power I m phi. Okay. So, phi star is basically 1. So, this probability basically will be independent of phi. Now, on the left for angular dependence, left this theta part. So, theta Lm star theta Lm plays the role of the directionality of the probability. Okay. So, phi part will not it will not participate in the angular dependence of the probability density, because it is 1. So, only we can look at this phi not phi theta Lm star theta Lm. So, this will tell us about the angular dependence of the probability density. So, angular dependence so this is the probability density, okay, angular probability density, and this is basically it is defined like this. So, what is theta? So, theta is basically angle between the angle of a direction with the z axis, right. So, if this is a nucleus, now from the nucleus means r equal to 0. So, if we take z axis, okay, now if you change that angle, if you change the angle, so means if you change the theta, so you are going a different direction. Now, in different direction, what is the probability to find the electron? So, if I draw like this, if this is the probability, this curve is showing the probability. So, then what does it mean? So, when this this angle theta this is 0. So, this it is 0, the probability is 0. Now, I am changing angle. So, this is say this is angle. So, at this angle, so this distance, okay, or here if we take this one, in this case it looks 90 degree, but it is not necessary to be 90 degree, any other angle. Okay. So, distance from this nucleus to that point on the curve. Okay. So, that is basically phi theta Lm star theta Lm. Okay. So, this meaning of this probability density is defined like this. So, this is this probability density, it is equal to the distance from the origin to the curve. Okay. So, these are the distance, the distance will tell about the probability of angular probability of finding the electron. So, here the complete directional dependence of this whole wave function is this. Okay. It is basically 3-dimensional surface obtained by rotating the diagram about the z axis through 360 range of the angle phi. So, it is independent. Here we have seen that it is this probability angular dependence, that is a probability, it is the independent of phi, it is independent of phi, means if you phi, which angle is phi? Phi angle is basically if you take the projection of this r on the xy plane. Okay. So, that projection it makes angle with the x. So, that is the phi. Okay. So, that is a phi angle with x axis, it is on a xy plane. Okay. So, phi can change from 0 to 360 degree, okay, where theta can change with z axis, it is 0 to 180 degree. Okay. So, when we will change theta from 0 to 180 degree. So, if it is varies like this, the density probability with theta is varies like this. Now, it is independent of phi, means now if you rotate it with respect to this z axis, if you rotate it, okay, so you will get 3-dimensional view. Okay. So, you will get the theta and phi dependence. Okay. So, that will be the probability, complete directional dependence of this of the wave function of this one. Okay. So, this angular dependence of the probability, that can be written in a new form. So, here I have written, so y Lm theta phi star y Lm theta phi. So, y Lm is basically here y Lm is basically theta Lm and phi Lm. Okay. These two angular dependence, this part one can write in this form y Lm theta phi. So, this y Lm theta phi is basically called the spherical harmonics, harmonics, and this is basically this will tell us if it is y star y. Okay, this will tell us about the probability from the origin in the direction of theta and phi, okay, up to the point on the surface. Okay. Whatever this we are getting, and this after rotation by 360 degree, whatever this will get the surface, okay, from the center or from the nucleus, distance from this distance at a point on the surface. So, that distance is basically the probability density, angular probability density, which depends on angle theta and phi. Okay. Y Lm, so we tell it is a spherical harmonics, it is a spherical harmonics. So, spherical harmonics y Lm theta as a function of theta phi. So, this is basically theta, it has two parts, one is theta part, okay, and another is phi part. So, in combined way, it is y Lm. So, now wave function, then we can write psi n Lm equal to r n L radial part and this angular part. Okay. So, that is angular part is y Lm. So, now few like radial part we have shown this few wave function for few value of L and N and L. Okay. So, in this case for spherical harmonics, so what is the form for different value of L and M? So, for first few value of L and M here I have shown you. So, when L equal to 0, M equal to 0, so this YLM means Y 0 0. So, wave function is this one. Okay. And then for L equal to 1, M is 0 plus minus 1. Okay. So, corresponding spherical harmonics Y 1 0 and Y 1 plus minus 1. So, these are the form. So, here it is it's the independent of for L equal to 0 and M equal to 0, it is independent of theta and phi, and this L equal to 1, M equal to 0, it depends on theta, only theta, it is independent of phi because M equal to 0. So, it is independent of phi. So, other one plus minus 1. So, e to the power plus minus I phi, that term has come. Okay. And yeah, similarly for L equal to 0, L equal to 2, M equal to 0 plus minus 1 plus minus 2, and corresponding spherical harmonics is given here. Okay. So, sine and cos terms are included, they are square. So, this they have some particular form that I have shown here. Okay. So, for other L equal to 3 and different value of M, these are the things. So, here you can see for yes. So, now if you know YLM, this form is like this. So, you will get the angular probability density taking y star. Okay. So, if I now plot it in graphical form, if you want to see, then angular probability density, okay, for small value of few value of L and M. So, here so phi star will be 1. So, only we have to concentrate about the theta. So, for M equal to 0 and L equal to 0, okay, if we plot probability density. So, it is the as we have seen, wave function is independent of, wave function is here independent of theta and phi, this constant. So, constant means it will be spherically distribution. So, it is this, and if you rotate it, okay, by 360 degree, so it will be sphere basically. Okay. So, this for M equal to 0, L equal to 0. Now, for L equal to 1, M equal to 0, what was the wave function? M equal to 0, L equal to 1, M equal to 0. Okay. So, this is the wave function. So, cos theta, it is the function of cos theta. Okay. Now, square of it will be cos square theta, right. So, probability density will be square of it is cos square theta. Okay. So, it's like this. So, distribution will how it is coming, So, let me tell you. So, what we have seen? So, L equal to 1 and M equal to 0. So, this term is basically is having cos theta. Okay. Now, probability will be square of it. Okay. So, if I plot it, this wave function, if I plot it, so this is z axis, this is z axis. Now, our theta is basically changing with this angle, they change from this z axis. So, it will make angle, defined angle. So, now you see if I plot cos theta, what I will get? If I plot cos theta term, you know this, what is the term cos theta. So, in this direction, okay, what is the value? It is 1, means theta equal to 0, it will be 1. Okay. So, I will get it is the 1. So, it is the 1 probability is this, square of it, it will be square of it also, it will be 1, right. So, now when it is 90 degree, this means it is like this 90 degree in this direction. Okay. What is the probability in this direction? 90 degree, it will be 0, right. So, it will be 0. Okay. So, at other direction say 45. So, it will be this value is 1 by root 2. So, square of it, it will be half. So, it will vary like this. Okay. 0 to 90 degree, it will vary like this. So, it has basically we have 4 quadrant, right, 0 to 90, then 90 to we have basically this first quadrant. So, 0 to 90, 90 to 180, 180 to 360, 180 to 270, and then fourth quadrant is 270 to 360. So, here just one. So, but in case of cos theta or sin theta, it will follow the same symmetry, right. So, basically for 4 quadrant you will this for 1 quadrant, if it is so, for other 4 quadrant it is the same. Okay. Same. Okay. So, for whole range of angle, okay, although it is we tell this theta varies from 0 to 180 degree, right. Why we tell? Because 0 to 180 degree, if you take 0 to 180 degree and then if you rotate by 360 degree, then it will basically it will cover the whole space, it will be sphere, right. So, so that means basically you are covering this whole angle. So, this angle here, this angle, and also one has to go this other angle. Okay. So, anyway, so this the dumbbell shape is coming, okay, because of this function. Okay. So, that is why we have drawn here like this, I have drawn here like this cos theta term. Okay. When L equal to 1 and M L equal to plus minus 1. So, in this case what is the wave function? In this case wave function is sin theta term. In this case wave function is sin theta term. Okay. Okay. This cos theta term and other M equal to plus minus 1, it is sin theta term is there, right. So, this sin theta term is there, right. So, for sin theta and this will go square it, this will go. So, sin square theta. So, basically, so it will be sin square theta, because this the plot is for sin square theta, okay, and for whole for 4 quadrant. So, at angle theta equal to 0 means in this direction when, okay, z direction. So, probability 0, right, because sin theta is theta equal to 0, it is 0, right, and maximum value is 1 sin theta when theta equal to 90 degree, when in this direction. So, it is the direction, it is with z axis is 90 degree. So, you will get maximum value 1. So, sin theta 1. So, sin square theta also 1. So, this is the maximum. Okay. So, this is the at 0 angle, this is the minimum, and 180 degree, that is the maximum. Okay. Sorry, 90 degree is the maximum. So, you are getting 0 to 90. So, this, so for other quadrant also from symmetry one can draw like this. So, it will be like this distribution, angular dependence. So, maximum probability to find out the electron in at the direction of 90 degree in case of M equal to plus minus 1. Okay. Similarly, for L equal to 2, now when you are going for higher value of L, so things becoming, so this your wave function also becoming slightly more and more complicated, but one can plot it, and if you plot, so it will be like, plot will be like this. Okay. So, here one thing you can see that from this plot one can see that for smaller value of, smallest value of m, okay, this m equal to 0. So, contribution is along the z direction. Okay. Maximum probability to find the electron along the z direction, right. And for highest value of L, for highest value of m, that is basically m is plus minus L. So, this probability is maximum along the on the plane. Maximum probability is basically on the plane which is perpendicular to the z axis, okay, means xy plane, to find the maximum probability to find the electron in the on the xy plane, right. So, here you can see for m equal to 0. So, maximum probability along the z direction, m equal to 0, maximum probability is along the z direction, and L equal, when m is maximum, that is plus minus L. So, in this case plus minus L. So, maximum probability on the plane perpendicular to the z axis, means xy plane. So, this can be x axis or y axis, whatever. So, that I will discuss. So, in basically for m equal to plus 1, if it is x axis, then m equal to minus 1, it will be along the y axis. Okay. So, it is basically, that is why we have written m equal to plus minus 1, it is basically on the xy plane. Okay. So, because z is perpendicular and z is perpendicular to the plane xy plane. Now, I am moving from the direction z to the xy plane. Okay. So, now variation when m equal to 0. So, maximum probability along the z direction. When m equal to maximum, that is plus minus L, then this maximum probability is on the plane, and in between value of L m, that is less than plus minus less than L, but greater than 0. So, there it is to find the electron, the probability, maximum probability will be in between these two, between the z direction and the xy plane. Okay. So, that is what is happening here in this case, okay, when m is plus minus 1. So, this is the maximum value, this is the minimum value, okay, and in between this is the value, and this it's neither along the x axis, neither along the neither on the xy plane, it is in between. Okay. So, here another things also, as I already described, that for m equal to plus minus L, where L equal to 0, 1, 2, 3. Okay. So, this concentration of the probability density more in the plane which is perpendicular to the z. Okay. So, that is why when L will be, value will be higher and higher, this you will get the more and more probability along on the x axis, on the xy plane, okay, which is perpendicular to the z plane, z axis. So, from here m equal to L equal to 0. Okay. So, this is the probability. Okay. And now, L equal to 1, and this for maximum value m equal to plus minus 1. So, it is on the plane, okay, on the plane. So, this it is also on the plane, but here just I tried to show you or tell you that this for all value of m which is equal to plus minus L. So, only you can find the, so the probability to find the electron or direction dependence is basically only on the xy plane, okay, or the plane perpendicular to the z axis. Okay. And this with higher value of L, this extends. So, up to longer the probability becoming higher and higher on this on a particular direction. So, this now imagine, now what we are seeing, or thinking that this or what we got from this analysis, that about the z axis, now probability to find the electron at different angle. Okay. So, in case of m equal to plus minus L, we have seen that this density, angular density or probability density is maximum on the xy plane, right, and along the z axis its probability is to find the electron probability 0, right, for maximum value of m, that is equal to plus minus L, and for minimum value of m, that is the basically 0, m equal to 0. So, this we are getting the this maximum probability is along the z axis, okay, and 0 probability to find along the on the plane. Okay. So, now we are so now you remember the space quantization in Bohr model, and after that this Rutherford model. So, they actually not Rutherford, the Sommerfeld, he introduced the space quantization. What is space quantization? Space quantization basically, so this orbit, okay, whether it is rotating in a orbit. So, that orbit it is on a plane. Now, this plane, now it can be, this plane is again in space, it is quantized. Okay. So, this plane basically it can be in any direction, means theta can be any value, but it was restricted because of postulate of space quantization. So, that means only this plane can be at particular orientation. Okay. So, that is the space quantization. Okay. So, here this orbit, okay, it is on a plane. Now, this angular momentum, that is basically L, is L related, okay, angular momentum. Now, this direction of angular momentum is perpendicular on this plane where this orbit is situated, right. So, that is the direction of the angular momentum. Okay. Now, here for space quantization for a particular L value. So, here I have shown you L equal to 2. For L equal to 2, I have shown the space quantization L equal to 2, space quantization m value will be 0, plus minus 1, plus minus 2. Okay. So, so basically this for so it will be quantized in such a way, that ml value will be 0, plus minus 1 and plus minus 2. Okay. So, 0 means ml 0, so that is the projection of the angular momentum, it is this direction. So, what is the value of the projection along a fixed direction, that is z direction. So, for this projection is this. So, this projection will be, this value will be integer value. Okay. So, plus 1 or plus 2 or 0 or minus 1 or minus 2. Okay. So, these are the 5 possible. So, now in this case L, when L equal to m equal to plus 2 means is equal to L, is equal to L. So, in this case this the projection is maximum, this, that means this direction of the angular momentum, the direction of the angular momentum is along the z direction. That is why we are getting maximum projection. So, for m equal to L, either plus L or minus L, only it is the parallel anti-parallel to z axis. Okay. So, that means in that case this direction of the angular momentum is along the z direction, means orbit will be on the plane, xy plane. If orbit is on the xy plane, then direction of the angular momentum will be along the z direction, right. That means for m equal to highest value, that is L, m equal to L plus minus L, in that case the orbit will be on the xy plane, because the direction of the angular momentum is along the z direction. Okay. So, probability to find the electron along the z direction is obviously 0, because this orbit is on xy plane. So, the probability will be maximum to find the electron on the xy plane. So, that is what from our analysis of the wave function, angular part of the wave function is telling us. Okay. So, this is on the, so this is perpendicular to this circle. Okay. So, this is on the xy plane, this is on the xy plane, and the next one. Okay. So, L, so for maximum value of m, which is equal to plus minus L. So, this is the so this wave function probability, angular probability density is telling this maximum probability is on the xy plane. Okay. So, which is nothing but just one can compare with the space quantization of Sommerfeld. Okay. So, this is all information basically we are getting from the wave function. Okay. And this is coming in natural way, but in case of Bohr Sommerfeld model, this everything also correct, but concept was introduced on ad hoc basis. So, just on assumption, this called basically postulates. Okay. And the same things we are getting when we are analyzing these wave functions, which we got from the Schrodinger equation for the hydrogen like atom. Okay. So, I think I will stop here. So, thank you very much.